Hey everybody, welcome to what is this? This is week 7. This week we're going to learn measures of variation, and then after that we're going to have a quiz this week. So I hope you guys are super excited and ready to go. Okay, let's keep going. All right, so in this lesson for this week, we're going to learn a lot about variation. Okay, so what is variation anyways? Variation is how much the data changes, really, or a change or difference in the condition or the amount or the level, in the data. Okay, so it's really just really all we want to know with variation is how much or with our data, when we're graphing our data or we're just trying to read the data. Okay, we want to know how much it varies. Okay, because that'll tell us a lot about what's going on with the numbers, or with our population or our sample. Okay, so how much does it vary? How much, or how consistent is the data? Maybe that's a better term. So for example, let me kind of give you a little bit of a different perspective. Okay, so what if, let's say, I have 2 different statistics classes and I gave the same quiz to each one, and just pretend that, well, let's just use our typical quiz scoring standards. All right, we all know that the quizzes are all worth 60 points, right? Well, what if the mean for the scores in both, for the quiz scores in both classes were 30? Okay, that's actually a really low mean. That's a pretty bad average. But just pretend, what if they were 30? Okay, does that really tell you what everyone is getting on their scores if you just looked at the average or the mean? It kind of doesn't, because if you think about it, if the mean is 30, right? And let's say in one class 1, we have the mean is 30 because we had a ton of people getting 60s, okay? Like a bunch of people got 60 or like 58 and such, and then we also had a ton of people that scored really bad. So we had a bunch of people getting like 5, okay, 3, really, really low scores, okay? Okay. So just pretend all of this, like the scores that we have, average out to 30. It could be like that. Or what if class 2, the second class that we have, the average is still 30, but what if it's the average, the mean is 30 because literally everyone just got 30s. Everyone scored 30 out of 60 on the entire quiz. Like the whole class just got that, Two different variations in both classes, right? But they have the same mean. So, sets of data, when you're studying, when you're looking at samples, you could have sets of data where there's the same mean, but it doesn't really tell you exactly what's going on or how consistent the data actually is and all that. That's why we really need to know exactly to what degree do they vary, okay? Are they all sticking really close to the mean? Or are they all just like, kind of on opposite ends of the spectrum, sort of like class 1, So that is why we need to sort of check our variation. So in this lesson, we're going to learn about the range, variance and standard deviation, and coefficient of variation. All right, let's get started. So first, let's learn about the range. What's the range? The range is the difference between the maximum value and the minimum value. Okay, so it's really easy to calculate. Basically, all you're going to do is you're going to look in your data set, and this is our example data set right here. So we're going to look in that, and we're going to go, okay, so the largest number, the maximum value, is the 78, right? And now what's the minimum value? Well, looks like it's the 21 right here. Okay. So what do? You have to subtract the smallest number from the biggest number, okay? That is how we find the range. So 78 minus 21 is 57. 57 is the range. Remember, you have to do that. You have to actually do the subtraction. Don't forget to actually subtract, because what a lot of people will do is they'll just find the max number and the minimum number, and then they'll be like, there you go, there's your range. Well, no, that's not the actual range. We have to actually see the difference between the large and the minimum value. Okay, so what does the range really tell you? It tells you a little something about the variety. Okay, it tells you the difference between the largest number and the smallest number. Like for example, if you have siblings, okay, and someone said, what is the difference between the oldest sibling in your family and the youngest? And maybe you would say, well, it's 2 years, okay, or 3 years, whatever, however many years it is. And then that would be it. That's your range, okay. Now, the range is not really useful. Okay, it's not that useful. It's a start. It's, it's good to do, and it will lead to other things, but the range really is not useful. It is not stable, nor is it resistant. Just like how, we've seen other measures of variation, measures of tendency that are not very stable or resistant. In the last lecture, same thing here. The range is not stable or resistant. Okay, because looking back at the same example, if the difference between the oldest kid and the youngest kid in the family is 3 years, what does that tell you about the ages? It doesn't really tell you anything. It just tells you that the age difference is that many years. But I mean, does it tell you that the oldest child is 21 and the youngest is 18? No, it doesn't tell you that. It doesn't tell you where the data actually is. It just tells you the difference between them. So any value can really throw that off. Okay, so it's not very stable. It's not resistant. Okay, so variance and standard deviation. These guys are friends. Like standard deviation would be nothing without variance. Okay, so what is variance? Variance is really just, it's looking at how much the data varies from the mean, okay? How different the data is from the mean. How much is it, going far off away from it, or how close is it to the mean, And then standard deviation, well, let's kind of break this down a little bit. So deviation is the action of departing, okay, of separating from your established or your accepted standard. So a standard deviation. We already know that the data is moving away from the accepted standard or the average. So we want to standardize that. Okay, that's the whole point of standard deviation. We take the variance, okay, because that's going to show how much the data varies from the mean, and then we standardize that. Okay, so I just kind of put this this picture here so that maybe you guys can kind of get an idea of, or maybe this will help you guys remember standard deviation. Okay, kind of like a deviated septum where the it's crooked. It's not it's more where it separates. It's more crooked. It's not standardized. Okay, so when you have a deviated septum, you can't really breathe properly. You sneeze weird, things like that. So this is kind of just bring it standard, okay? Allowing your numbers to get to be more standardized so that we can understand them a little bit better. Okay, so what are the formulas for variance and standard deviation? Well, variance is just going to be the calculation of how much the data varies from the mean, right? And then the standard deviation, how the standard deviation standardizes the variance is you're going to take whatever numbers you have from the variance, and you're going to take the square root of it. Okay, and that's how we standardize it. Okay, so looking at formulas for variance and standard deviation. First of all, I just want to point out that the formulas for sample variance and sample standard deviation are different from the formulas for population variance and population standard deviation. That being said, we almost don't use population variance and population standard deviation much at all. And the reason for that is because I told you guys before that using the whole population is just not as common. We usually don't take census, and we usually don't use census data for our studies. We normally are going to create a sample. Okay, so that is why the sample variance, sample standard deviation is a lot more common, and you're going to be using that a whole lot more often, more than likely. Unless, who knows, maybe you'll have a job in the future where you do actually check census a lot and extract a lot of data from the actual population. Also, there are two different ways of even doing the formulas, okay? Okay, for both sample and population, but also there are two, for both sample and population, sorry. So we have the defining formula, and then there's going to be the computational formula. We're going to look at the defining formula, okay? We're not necessarily going to get too much into the computational formula because that's a little bit more difficult and maybe a bit more confusing, okay? And I like to keep things simple. Maybe later on in the future, if you are working on something super complicated and you're a really big deal and your research is insane, you might be wanting to use the computational formula, and that's okay. But for the most part, we're going to be using defining formula because normally when you get out into the world and you conduct your studies, a lot of what you're going to be doing is just going to be plugging numbers into a software program that is going to give you everything that you need. Okay, so we really just need to understand how these formulas work. Okay, so now we're going to look at formulas. So just in case you didn't notice yet, this is a sample defining formula. We're looking at defining formulas, and we're looking at the sample ones right now. Okay, so here are your formulas for the sample variance and then the sample standard deviation. I know they look kind of scary, but let's kind of break it down. We're going to actually go through this. But first of all, do you see how it says sample variance equals s squared right there? Well, s squared is like the symbol for sample variance. So anytime you do see an s squared, that's what they're talking about. They mean sample variance. And you can also write that in your work as well. You can go s squared equals something, and then everyone is supposed to know that that is code for sample variance. Okay. Also, there's another way you can write the code for variance. Sometimes people just will write VAR. Okay. So that's also another way that you can do this. So anyway, on the numerator, I know you guys see the sigma symbol right here, and of course you guys know that that means sum up. So we're going to be summing up something in the numerator here, and then the denominator, which looks pretty darn easy, is an n-1. So don't worry about this. Don't let this numerator scare you right here. We are definitely going to run through this. Now let's look at the sample standard deviation. Okay, notice that the code for standard deviation is S. Okay, wow, just S. Well, remember that square roots and when you square something, those are opposites, right? So, and remember that we also said that standard deviation is the square root of sample variance. So if you were to do this, if you were to take the square root the sample variance, you get S. It's not writing. There we go. You get that, right? So that just kind of gives you, I hope you guys kind of understand why it's just S and nothing fancy. Because if we're making this S squared, and this, the standard deviation is the square root of that, then of course it's just going to be straight up S. Anyway, so I hope you guys can also see that in the formula, all that is done here is this is the exact same thing as sample variance, but we take the square root of the whole darn thing. Okay? Okay, so now we're gonna go ahead and break down the equation and see how to work it out. So the first part, that circled part right there, this is actually called the sum of squares. Okay, now let's actually get in there and figure out how to work that top part, because this is the most complicated part of your sample variance, the sum of squares. Okay, let's do it. Okay, everybody, it's the moment we've been waiting for. We want to figure out how in the world to work this crazy portion of that formula right here. All right, so here we're going to go ahead and uncover the mystery in the next few slides. Okay, so just so you guys know, this little equation here, don't necessarily need to memorize it, but when you do see it, just know that this is another way of saying sum of squares. Okay, so let's you guys obviously do not have to write out a whole graph like this when you're doing the sum of squares, but this is the best way I can show you how it makes sense. Okay, and honestly, this is, if I'm going to do something by hand, if I'm going to use this equation and do some work by hand, this is what I'm going to do. This is what people like me still like to do. Okay, because it's you understand it a whole lot better. So for your homework, for assignments and things like that, I highly recommend to just write everything out, create a little graph like this so you understand what you're doing and where the numbers are going. Okay, so anyway, let's come up with a cool, fun, fake study that we're going to do for this example. Okay, so let's imagine that we are conducting a study on patients who go to the lab to, draw labs, okay, get their blood drawn and stuff. And we want to know how long it takes for them to wait to get their service, to get their blood drawn, okay? Because let's say we're in the business of customer service. We want to make sure that we are providing our patients with great customer service and that they're in and out. They're not sitting there waiting. So we want to conduct a study and figure this out. So what we did was we asked the patients how long they actually waited to get their service. And these are the numbers, the minutes that we got. Okay, so you can see by looking at the data, probably, I would assume maybe around this time, it's like maybe we didn't have very many patients during that time, so the patients were able to go in and out, and maybe during this time it could have been like while some of the staff members may have been on lunch break, or maybe we just had like a rush of patients, so they didn't get in and out very quickly, or something is going on, right? Anyway, so next step, what we're gonna do with our fake data right here is we're going to go ahead and put that in column 1. As you can see, we labeled these columns. So 1 is going to be X, which is just your data, the number of minutes. Okay, column 2, we're going to put X minus X bar. Remember what X bar means? X bar is this. What does this mean? It means the mean. Okay, it's your average. Okay, so for this column 2, that's going to be your data, your reading or your value, right, minus your mean. Okay. And then in this column, I hope you can tell that this is going to be whatever, that value minus the mean is. squared. Okay, so let's go ahead and do that. First step is go ahead and put all of your readings in your X column, and that is what we did. And then we found out that the total is going to be 36. And remember that this symbol right here, this backwards looking triangular 3, the sigma symbol, right? That means sum, okay? So that means you're adding things up. So anytime you see that, remember, sum, you're summing up stuff. Okay, so so basically this is the total, okay, right there. Okay, next, what we're gonna do is go ahead and go through the entire table, okay, in each little, in each box, and just go ahead and fill it in. So, start with the first one. We had 2 as our value right there. Now, what we're going to do in the second column right here is you minus 2 from 6, because remember, 6 was our average. And how do we get that, or how do we get our mean? Well, we calculated using our total, right? And then we divided that by 6, because we have 1, 2, 3, 4, 5, 6 total values here. Okay, so our X bar is 6, because 36 divided by 6 is 6. Okay, so we did figure this already out. That is why we are minusing each one of these values right here by 6. Okay, so just go ahead and run through and do it. It's okay if you have negative numbers. Don't freak out. Okay, so 2 minus 6, negative 4. 3 minus 6 is negative 3. 3 minus 6 is negative 3. 8 minus 6 is 2. 10 minus 6 is 4. And then 10 minus 6 is 4. So we got all of our X minus X bar values right here. Now we're on the next section. Okay, right here. We're in column 3 now. Now this one is going to take everything you did in column 2 and square it. So basically, negative 4 squared is 16. Negative 3 squared is 9. Negative 3 squared is 9. 2 squared is 4. 4 squared is 16. And then 4 squared is 16. So then what we're going to do is add everybody up. Okay, and that's how we get the sum of our squares. So we add up all the squares, okay, and we get the sum of our squares, which is 70. Boom! Unsolved the mystery right there. You're welcome, everybody. Okay, so now that we did all that, so we did the top half, right? We did the top half, and that was 70. Okay, or top half numerator is what I should be telling you guys. Okay, so next we need to figure out what goes here. Okay, and what does go here? Well, and this is how many values we had. Okay, and how many values did we have? We had 6, remember? We had 6 readings total. So that is why n equals 6. Okay, so just to fit that into the equation and solve the denominator, we would just take n minus 1, plug in 6 for n, okay, and then we'll say go 6 minus 1 equals 5. So then we have, so now in this equation we have 70 divided by 5. And what does that equal? That equals 14. All right, so we solved it. We did it. The variance equals 14. Wow, good job, everybody. Great, so after we figure out the variance, next step would be to figure out the standard deviation, right? Right. Okay, so, and the last slide we already figured out the variance. The variance is 14. Next, remember, all we have to do to figure out the standard deviation is take the square root of the variance. Remember? So I know this equation looks crazy, but we just did it. So all we gotta do now is plug 14 in for this section, because we already figured that part out. Okay, so 14, the square root of 14 is 3.74. Of course, you can do this in your calculators. There are no rules against calculators. So there we go. Okay, so remember I said that I was going to show you the differences between using a sample defining formula, okay, of sample variance and standard deviation, and doing the population defining formulas for population variance and then population standard deviation. So let's just look at this really quick and compare and contrast the differences. There are some tiny little differences here and there. So first of all, let's look at this symbol. Of course, we have an S for sample variance, an S squared, and then we have an S for standard deviation. Well, over here, we have this symbol that looks like a really fat 6 or a jelly roll, however you want to picture it. Whatever you see, that's what it is. But anyways, what this actually is a lowercase sigma. Okay, remember this sigma right here? This is a capital sigma in Greek letters, and this one is a lowercase sigma. Okay, so, you know, there's that difference, first of all. It doesn't really mean anything, it means the same thing. They're just symbols. But when you do see this, okay, when you do see it with the jelly roll with the, you know, jelly roll squared, okay, or a really, really obese 6 squared, that means population variance, and it does not mean sample variance. Okay, that means you're looking at the entire population, the census, instead of just a sample in your study. Okay, so if you're doing a study where you are actually gathering information from the entire population, of course you would use this. But if you're doing a sample, and most of the time, most studies, you know, you're going to be using sample. So, but you know, that's the difference. If you happen to be doing population, of course, use the obese 6 symbol squared, and that would be what your standard deviation symbol looks like. Okay, now look over here. Remember, mu was the symbol for the mean. Okay, we already did this in like a previous lecture, but again, mu, we know about that, and we know that that is the symbol for the mean. Now look over here. Okay, n, which we know, okay, yes, that is like the number of the values that we have available in our data set. So we know that. And of course that means that's how many, the values in your data set, that obviously means that's the number in your population. Okay, so population number right there, that's your capital N. But notice that we're not, this is the main difference. Okay, we are not subtracting 1 from it. Okay, we're just going straight out N. Okay, and well, it kind of actually makes sense to do it like this if you really think about it. Okay, because I mean, it kind of wouldn't even matter actually if we subtracted 1 from N, the total population, because the population is going to be so huge. When it's a sample, it's a, you know, it's a small amount of numbers. Okay, it's a small amount of participants, it's a small amount of values that you're working with. When you're working with populations, it's going to be, you're going to be looking at huge numbers, okay, large data sets. So minusing 1 from it wouldn't even hurt it at all. It wouldn't do anything to it. So there's that. So let's look at let's look at the formula for the coefficient of variation. Okay, if you go ahead and look over here, just like how with standard deviation and variation, you are going to have a totally different equation for if you're doing a sample and if you're doing a population. Okay, or you know, taking census data, right? So anyway, let's look at the formula. All right, so basically, this is actually really, really simple. All right, you guys know what this is, right? This is your standard deviation. So basically, you know you have to do those calculations before you, you know, prior to this, so that you will be able to get your coefficient of variation. So you definitely have to figure out your sum of the squares, your variation, then your standard deviation. And again, deviation, I apologize profusely for my terrible writing. I hope you guys can understand that that's a standard deviation. And down here, we got x bar. So what was x bar again? That was the mean, or the average, whatever you want to call it. But in statistics, we're supposed to say mean. So then you go ahead and look at the same equation down here for the population. It's really the exact same thing. You take your standard deviation. Remember the symbol for standard deviation in a population equation is the jelly roll or the OB6, whatever you want to call it. And then mu is also the mean. So it's the exact same equation. There's nothing different really. It's just different symbols. And of course, so anyway, in the equation, you're going to take your standard deviation, divide it by the average or the mean, and then you multiply it by 100. And that is going to give you a percent. Okay, like I said earlier, the coefficient of variation is always going to be expressed as a percent because this is going to show like a proportion. Okay, this shows like how much the proportion of the data varies to the mean. Okay, so I hope that makes sense a little bit. Let's go ahead and look at an example. So let's look at an example. I'm not going to give you guys an entire problem, data to actually look at. For this example, we're going to pretend we have patients and it's just, well, anyway, here's some made up standard deviation and mean that we're going to apply to this equation and to try to make sense out of it. Okay, so for the first study, made up fake study that we did with our fake standard deviation and mean. Let's go ahead and put this together and see what we get. All right, so your standard deviation was a 4, so we put 4 right there. Then your mean, your x bar, was an 8, so we're going to put 8 right there where it goes. Then go ahead and multiply that by 100 and we get 50%. Okay, then in our next fake example, okay, we have the standard deviation is at 3.74. Okay, and then our x bar or mean is at 6. So go ahead and plug those into the equation. 3.74 divided by 6, and then we'll multiply that by 100. Okay, and then we end up getting 62%. Okay, so what's the difference between these two numbers, these two coefficient of variations? Well, basically, since this is a higher proportion than this, we can say that, well, it had happened because the standard deviation here is larger in proportion to the mean. Okay, that's why we ended up getting a 62%. Whereas over here, okay, yes, the standard deviation is a 4, but look at our mean is also a lot higher. And so in this section, the standard deviation is actually a little bit less in proportion to the mean than it is over on this side. If you really think about it, that's true, because what does this equal? 1/2. And what does this equal? Well, I don't have a calculator with me, but you know it's more than 1/2. Okay, so definitely. Anyway, back to what I was saying. When you have something like this, this basically means that it's more not stable. It's less stable than this one, okay? This one means, just given the fact that it's a little bit higher in comparison with this one, it means that there's more, the data is a little bit more spread out in this one, okay? In the one with the larger proportion. It means that the data is a little bit less, it's not as stable, it's kind of, going all over the place. It might be a little bit more spread out. So, it deviates a lot from the mean compared to the first one. Since it's a little bit less, that we would say that that one's a little bit more stable. The different data positions, the different data values are probably closer to the mean. Okay, so can I tell you a little bit more about what's going on with the data there? With where the action is. It's going to give you a greater picture, I guess, with what's going on there. That doesn't necessarily mean that this doesn't give you a greater picture, because there can be situations where this would definitely make a lot of sense. And it's not due to, weird occurrences in the data or in your study. It may just be because of, certain circumstances happened and provided different types of data readings, and that is why this looks a bit more unstable. Now, when you go further, you can definitely interpret this a lot more in a deeper way, but we're not going to get too much into that. Just know that, like, the greater this is, the more unstable your data is, the more your data is actually deviating and it's further away from the mean. Okay? And of course, the smaller it is, the more stable your data is, the closer your data values are to the mean. So that's the main idea there. Okay, so there was this guy named Chebyshev, and he figured out a cool, significant way to work with your upper limits and your lower limits and your standard deviation and your mean, and it will lead to something that's very useful and significant in statistics and when you're analyzing your data. Okay, so let me just kind of walk you through a little bit of his thought process before we get into what this can be used for, before we get into the actual theorem. Okay, so first he was thinking that we can take, if you have an x-bar or a mean, and you have a standard deviation, you can create your lower and upper limits, okay, by subtracting the standard deviation and then adding the standard deviation to the mean, okay? Now, remember back when we were finding our, our class limits, when we were going through our frequency tables and we were you're figuring out your class limits and all that, and we use that equation. Well, this is going to lead to that. So think upper and lower limits. Remember go back and look if you forgot. But so anyway, and then you can also do this whole thing, this whole thought process and all that. This applies to population version and also sample version. Okay, so don't get that confused. You can do it both ways. So anyway, all right, so if you had a mu of 10, or remember what mu is, the mean, of 100, and then you had a standard deviation of 5, right? Pretend that's what we had. I don't know where these numbers came from. I don't know what they mean, but pretend we have a mean of 100 and a standard deviation of 5 from some data set. So if we subtract one of the standard deviations, which is 5, from 100, then we get 95, because 100 minus 5 is 95, right? And we can use that as the lower limit. And then we can add one of the standard deviations to 100, okay? Which would be 100 plus 5, right? And you would get 105. And we can use that as an upper limit. Then we could even try this by doing, by using 2 standard deviations. So basically 2 standard deviations in this situation would be 2 5s or 10, or 2 times 5, right? So 2 times 5 minus 2 times, yeah. So you would be able to subtract the 10 because you did 2 times 5, right? Which equals 10. So you can subtract the 10 from your mean, and then you can also add the 10 to your mean. And you can get your lower limit and upper limit that way as well. Okay, so he realized that, you could apply this rule, this set of rules, and you could actually interpret these limits in a really useful way. So we're going to get into that. So Chebyshev's theorem, all right. So piggybacking off of the previous slide, he already figured out how we can, create upper limits and lower limits, right, in your data set. But then he figured out that if you use this this method, it also explains it explains at least like what percentage of the data values would be in between those two limits. Like you have your upper limit and then you have your lower limit. Pretend, I don't know, maybe your upper limit is 6, your lower lit is 3, and then in the next set it could be like 2 and what would that be, 0 or something, as an lower limit, upper limit, lower limit, whatever. Anyway, so by using this theorem, we can tell what percentage of the data values that you have in your data set are going to fall within or in between the upper limit and lower limit of the values. So for each upper limit and lower limit set that you have, this will be able to explain what percentage of the data is falling in between the 6 and the 3, or falling in between this 2 and 0. Like what percentage of your data is, in between these values. That's pretty cool. I hope you guys aren't getting confused about this, but so it's pretty amazing. That's really useful, actually. Okay, and the thing is, he wanted this to work out for all the distributions, because we're looking at normal distribution right now, and we're always thinking normal distribution. Okay, but he wanted this to work out for all of the distributions. So he used this formula to figure out the percentage that was based on the standard deviation. Okay, so how the formula he came up with, he used K, okay, to mean the number of standard deviations, S, that you're going to use in your equation. Because remember the last slide, you can use multiple standard deviations, not different standard deviations, but whatever the standard deviation is that you calculated, you can use that a couple times. Okay, you can use one of those standard deviations, or you can go ahead and use 2, you can use 3, however many you plan to do for this data set. K is that number that corresponds to how many standard deviations you are going to use. Okay, so what he did was he went, okay, K is going to equal the number of standard deviations that we're going to use. Okay, so basically this equation is 1 divided by K squared, okay, or 1 minus 1 divided by K squared. And that is going to equal the percentage of data between X bar minus K and X bar plus K. And remember, X bar minus K, X bar plus K, this is your lower limit, and this is your upper limit. Okay, so this equation is going to tell you the percentage of the values that are between your lower limit and upper limit. Okay, so I hope that makes sense. For example, like let's say you decided that you're going to use 2 standard deviations. So K would be 2, right? So if K is 2, well, if K is 2, then it's going to look like this, right? And then, so now we're going to get 1 minus 1 over what's 2 squared, that would be 4. And then 1 minus 1/4 would be 3/4, or 75%, right? So basically this means if you're using 2 as your standard deviation, or 2 as like the amount of standard deviations that you are going to use for your lower and upper limits, then 75% of your data between your lower limit and your upper limit, or 75% of your data will fall between your lower limit and upper limit. Okay. All right, so now let's kind of like dig a little bit deeper into this. So that's what it looks like whenever we use 2 or as our k, or like 2 meaning we're using 2 standard deviations. Okay, we will always be getting 75%, which means that 75% of the data set will fall between whatever our lower limit and upper limit is. And remember in the previous example, when we calculated, what was it? Our mean was 100, and then our standard deviation was 5, I believe. And then so we said if we were going to use 2, that would mean we're going to use 2 of these 5s, which is 10, of course. So it would be to find your lower limit, it would be 100 minus 10, okay, which would be 90, right? And then to find your upper limit, we would go 100 plus 10, and that would be 110. So these are your upper and lower limits for that situation, right? And then since we use 2 as our k, because we use 2 standard deviations, that would mean that 75% of our total data set would fall between 90 and 110. Okay, does that kind of make sense a little bit? So 75% of our data falls between this. Now, if we wanted to do 3 or 4, we definitely could. Let me show you how if we would use k equals 3, where we would, basically that means you're using 3 of those standard deviations. Okay, so if we're using 3 of those standard deviations, where k equals 3, and we're using the same 100, and where your mean is 100, and your standard deviation is 5. Okay, so if we're going to use k equals 3, that means that we're going to use 3 5s, or 315, or it's going to equal 15. Okay, so 15 is what we add and subtract to the 100 to figure out what our upper and lower limits are going to be. So you can go 100 plus 15, and that's going to be 115, right? That's your upper limit, and then you go 100 minus 15, which is going to be 85. Okay, so you would have an upper limit of 115, okay, and then we would have a lower limit of 85, and then if we're going to figure out our which percentage of the data falls between these, we would go 1 minus 1 over 3 squared, okay, and then that would be 1 minus 1 over 9, okay, and then let me just get a calculator because I don't want to do the rest of it by hand. All right, 1 divided by 9. Okay, so I got 80.889, right? And to turn that, we have to multiply that into we have to multiply this by 100, to make it a percent, which means that we're going to get 88.9%. So 88.9% of our entire data set is going to fall between our upper and lower limits of 115, and 85. Okay, so that's kind of how it goes. The thing is about this theorem is that you will only need to really calculate this if you really have to. If you have some unusual K, or actually you really don't actually, because the thing is that regardless of what your data is, okay, K will be whatever you choose to be for K, you're gonna get the exact same percentage no matter what. Okay, so anytime you choose 3 as your K, okay, you're gonna use 3 standard deviations to find your upper and lower limits. Well, your percentage, okay, is always going to be 88.9%. And if you ever decide if you like to use 4, so you're going to use 4 standard deviations for this exercise, then you will always get 93.8% regardless of what is in your data set. Okay, because this is separate from that. Of course, you'll have to do the math to figure out your upper and lower limits, but when you figure out the percentage of the data between each your upper and lower limits, that will always be the same thing. Okay, so now does that mean you have to actually memorize all the percentages? No, I wouldn't do that. You can definitely memorize them if you find it useful. You can make yourself some flashcards if you think you're going to be dealing with this a lot and you're not going to have a computer in front of you, then yes, memorize them. But in the future, when you're working with this theorem, just know that Google is always there for you and you can look up anything. So you don't really have to do the math. Just know how these equations work. Just know how this equation works, why it works like this, and what it means. Other than that, go ahead and look up the percentages when you need them. All right, guys, now let's learn how to interpret this data, or learn how to use this information. Okay, so I don't remember if this was the correct numbers from that previous example when we were from the fake study where we were taking people's readings from the waiting room, but we're just going to pretend it is. Okay, so please don't fact check me. Anyway, so pretend from that study our mean, or our X bar, was 6. Okay, that was our average, the average time that people were waiting in the waiting room, right? And then our standard deviation is going to be 3.74. Okay, pretend we calculated that with our data. We already got these answers. Okay, so now we're going to use this and try to interpret the data using Chebyshev's intervals. Okay, so let's say if we were going to use 2 Ks or 2 standard deviations, that would be this one. So let's look over here. We already know that this is going to be a 75% limit. All right, because we already know if we use 2, we get 75%. That means 75% of the data falls between your lower and upper limits. What does that even mean? Well, let's actually figure out what your upper and lower limits would be if we were to do this. Okay, so this was your standard deviation. And remember, in this equation, we are using 2. So 2 standard deviations for this situation, which would mean that 3.74 times 2, okay, is 3.74 times 2 is going to be 7.48. All right, so that's us using 2 of these standard deviations. All right, so that means we have to add 7.45 to the mean, to the X bar, and then we're going to subtract 7.45 from your X bar. Okay, so if we were to subtract if we were to subtract 6 minus 7.45, we would get negative 1.48. Okay, and then we are going to, when we add 7.45 to 6, we get 13.48. Okay. I'm sorry, this was an 8, not a 5. I did that wrong, my bad. But anyway, so you get those answers. That would be your lower limit and your upper limit. So this means, okay, if we go into your interpretation of what that means, that would mean at least 75% of all of the data that we captured, you know, when we were taking everyone's time who were sitting in the waiting room of all those patients. Okay, at least 75% of those waiting room minutes readings that we caught are going to fall between negative 1.48 and 13.48. Okay, so let's try the other ones really quick, just in case you didn't quite understand how the whole interpretation of that data means. Okay, so same, we're going to use the exact same data. This is our standard deviation, this is our mean. Okay, same thing. Now let's find some new upper limits. We're going to use three standard deviations, right here, which means the percentage for that will be 88.9%. So let's figure out how we got our upper limit and lower limit to be negative 5.22 and then 17.22. So what we did was we went, all right, since we're going to use 3 standard deviations, that means we have to go 3 times 3.74. Okay, now what is that? Let me calculate it for you. 3 times 3.74. It equals 11.22. Okay, so that means that we have to add 11.22 to 6, and we also have to subtract 6 by 11.22. So how do we find, let's find our lower limit first. That means we're going to go like this, 6 minus 11.22, and that will equal 6 minus 11.22, negative 5.22. And then we are going to do the same thing with our upper, well, we're going to find our upper limit and we're going to add. So we go 6 plus 11.22, which is 17.22. Aha, we got him. There we go. Now what does that mean? Let's look over here at the interpretation. That means that at least 88.9% of the data, remember their waiting room minutes, are between negative 5.2 minutes and 17.22 minutes. Okay? So just in case you didn't catch that, let's do the last one, the third one. Okay, where we're using 4 standard deviations. Okay, real quick. If I can erase this. Okay, so we're going to use 4 standard deviations for the same one. Okay, let's see what happens. This is our standard deviation. This is our mean. So how we're going to start this problem out, we're going to find our upper and lower limits. Okay, and so it's going to be 4 times 3.74. All right, and let's see what that equals. That is 14.96. Now we're going to take this number and add or subtract it to our mean. All right, so let's find our upper limit real quick. The upper limit is going to be 6 plus 14.96. And so that is going to equal 20.96. 20.96, and then let's find our lower limit, which is going to be 6 minus 14.96. So what is that going to be? That is going to be negative 8.96. All right, so here we have our upper limits, and then we have our lower limit, and yep, checks out. That's what we got previously. All right, so what does that mean? Let's look at our interpretation. At least 93.8% of the data, in waiting room minutes will fall between negative 8.96 seconds or minutes and 20.96 minutes. Okay, so that is what that means. You can obviously apply this to other data sets and other situations, other studies that you guys do, but that is pretty much how this works. Okay, so in the end, this is basically what it all means right here. So if in the data set, like if we had 100 patients that we looked at, we checked, we were taking their waiting room minutes, okay? This would mean that at least 75 patients would have waited between negative 1.48 minutes and 13.48 minutes. So that's like a good portion of like the entire data would have waited that long. If we had, if we're looking at the next level up, the 88.9 percentage, that would mean that at least 88.9 of your patients would have waited between negative 5.22 and 17.22 minutes. And then if we go even further, we can say that at least 93.8 patients would have waited between negative 8.96 and 20.96 minutes. So that's pretty much what that is. If you really look at this, or really think about this theorem, it's we're not, here, let me move forward a little bit. We're not really going to be using this too much in healthcare, okay? Because as you can probably tell, we were given negative minutes, okay, for this data set. So it doesn't really, it's not practical for a lot of our data, especially like in healthcare. So using this, not too helpful, but it can be, just depending on what you're actually doing. If it makes sense for your study, for what you're doing, then yeah, okay, we're gonna use this. But also you have to keep in mind that this theorem is quite loosey-goosey, okay? It's not giving you an exact percentage of how much of like what proportion of the data falls in between, certain upper and lower limits. It's giving you at least, and it's giving you like insanely large ranges, between your upper and lower limits. If you haven't noticed already, those are huge ranges. Remember the previous slide, we were going from negative this all the way to like 20, okay? 20 minutes. That is an enormous range. I know more than likely all or most of the data will fit within that range. That's great, but it's not even practical to use that, especially for this particular study, because how can you get negative minutes? So this is not always going to be the best thing to use, especially in healthcare. Okay, but just so that we all know, this theorem works for any kind of distribution. Okay, so it's not going to be just normal distribution. You can do your skewed distributions, your bimodal distribution. This works for all of it. You can use it on anything. Of course, it's very loosey-goosey. It's very generic. Huge ranges between your upper and lower class limits when you use this. Okay, so it's not, sometimes it's great to use, but in healthcare, it's definitely not that great to use usually. So I've never really used much of this, just in school, of this particular thing. But it is good to get your mind to start thinking about this, because later on we are actually going to, there are better ways to figure out more accurate limits and percentages of the data. Okay. So it is just good to understand how this works. All right. I will see you guys next time.